even light is a form of wave. But sound is also a form of wave. So we're going to show you here a wave on a string. And so this string is a little like the string on your guitar or on a violin. On one end we have a weight just to put it under tension. On the other end we have a little vibrator that goes up and down very rapidly, about 50 times every second. And that's making it vibrate. And if we adjust it just right, you can see it vibrates so that there is a large vibration here and here and here, and very little vibration here. These are called nodes, and these are called antinodes. Now I can demonstrate that a little better using the strobe light and adjusting the frequency of the strobe light so it is synchronized with the frequency of the vibrating string. And you can see it makes the string appear to come to rest. And that's because we're illuminating it at the same frequency that it's vibrating. But you can be assured that the string is vibrating very, very rapidly. Now, that's a form of wave that we call a transverse wave. That's not what a sound wave, or sorry, that's, transverse wave. Sound is not that kind of wave. It's what we call a longitudinal wave. When I'm talking and you're listening, the air between my lips and your ears, or actually between the speakers and your ears, is vibrating. But it's not vibrating up and down like that. It's vibrating back and forth. And that's called a longitudinal or compressional wave. Now I have one other sound demonstration here. Here I have a little gadget that makes a sound. I'm going to turn it on and see if you can hear the sound. It's not very loud. Can you hear that? Except I'm going to have to turn my microphone. Now I hope you noticed a peculiar sound. It went woo, woo, woo. When it was coming toward you, it was making a high pitch. When it was going away from you, it was making a low pitch. And you may wonder why I turned my microphone off. And that's because I was right in the middle. It wasn't coming toward me or away from me. And so the sound that I was hearing, and that would be picked up by my microphone, would not hear the sound that you heard at all. And that's something called the Doppler effect. And you're probably all familiar with it. If you go out on the highway sometime, and cars are coming by, I notice that they honk their horns a lot here in Egypt, and if a car is coming by and honking its horn, you know what it sounds like? It sounds like, meow. You've heard that, right? So when it's coming toward you, it has a high pitch. When it's going away from you, it has a low pitch. And that's the Doppler effect that you're all familiar with. And that's how the police measure how fast your car is going. Not using sound wave, but using radar, which is another form of wave, an electromagnetic wave, but it also exhibits the Doppler effect. Okay, so there are many things that have to do with the physics of sound, but I want to tell you another kind of wave, and that has to do with electricity. Electricity can also form waves. We call them electromagnetic waves. And there are many ways to make electromagnetic waves. And we have here one little gadget called a Tesla coil. And if I'm able to plug it in back there, turn it on, it makes a very high voltage, high frequency electric voltage. And it produces about 50,000 volts. And it's basically a transformer. It has one coil of wire that is at low voltage, and then there's another coil with many, many turns on it that steps the voltage up to a very high value. Now to convince you it's really doing something, I'm just going to take this fluorescent light, very similar to one that perhaps you have at home, or at school, or at work. And you see, I don't even have to touch it, I just have to bring it near, and you see how it lights up. And that's because there is electricity in the air. These radio waves produced by this are absorbed here, and the electric currents pass through the air, they pass through this tube, they pass through my body, right down to the floor and back to the ground. So I'm part of the electric circuit that is formed when we do this. Now here I have another light bulb this to the terminal of the Tesla coil, and you see the sparks that form inside. And those are little like bolts of lightning, little tiny bolts of lightning. Now, I should caution you, of course, electricity is potentially very dangerous. And this is safe, first of all, because the current that it can supply, the number of electrons that it pushes through your body is very, very small, and furthermore, the frequency is very high. It would certainly not be safe to do this with the kind of voltage that comes out of the wall socket you have at home. This is at a frequency of maybe 100,000 cycles per second, whereas what comes out of the wall socket is a mere 50 cycles per second. So it's safe because of the very high frequency and because of the very low current. Now that's an alternating current. I have over here a device that will make a very large direct current, or a DC voltage, and it's a device that we call a Van de Graaff generator. And it's a large dome, and below it is a rubber belt that goes around, and at the bottom the belt collects electric charge, and it carries it up to this dome, where the dome begins to acquire electrons. And when I turn it on, you will see these strips of paper begin to rise up. Now, sometimes we have a volunteer come down with the right kind of hair, and we make their hair stand up. But we won't do that today, but just pretend this is someone's hair. And you may wonder why that happens. And it happens because all of those little strips of paper are negatively charged. And charges of a like sign, two negative charges, repel one another. And so they try to get as far apart as they can. So they stand up like that. Now, we have over here another gadget.